I wish to thank the organizer to have given to me the opportunity of celebrating the 70th birthday of Danny. Dear Danny, I want to present you the dynamical calculations that is used to perform high-resolution electron microscopy images. And throughout these calculations, we describe structural models. From the very beginning, electron microscopy was the major tool that is used at the beginning of the discovery of quasicrystals. First observations performed in 1982 by Danny Sheshmans on solid order with overall icosahedral was diffraction patterns along the three orientations of the icosahedral, and this was with image dark field and later with high resolution images, the most convincing proofs, experimental proofs that icosahedral quasicrystal exists. Simulation take more time to emerge because people use the standard program on quasicrystals and with large cell, unit cell, and they compare the local symmetry to the symmetry of the parent quasicrystal. But we present dynamical calculations without any artificial periodicity with large superstructure cell. Although X-rays and neutron diffraction give us more good data, the simulation is a good tool to study both structural model and to study defects with a correct model. Now I show you two high-resolution images. The first high-resolution image is performed in 1985 by Danny Sheshman, Dennis Gracias, and John Kahn on aluminium manganese. At that date, this image shown the first evidence of the first microscopic evidence of quasi-periodic order. Below, you have a high-resolution image performed on aluminium lithium copper in 2002 by Kono, Oshuna, and Iraga, and you can see that the resolution was better. On the top of the slide, you have a sample of crystal or quasicrystals, and below you have the corresponding reciprocal space where the incident beam K0 has a component in the diffraction plane that is a key and a perpendicular component along the Z direction. And this incident wave plane diffract in the direction kg. And you have here omega, large omega. This is the center of the eval sphere that projects on small omega, and K is a vector that connects small omega to O, that is the origin of the reciprocal lattice. And then you have Q that is equal to K plus G, where G is a vector of the reciprocal lattice. On the right, you have two diffraction patterns, calculated diffraction pattern. On top, you have a diffraction pattern of a standard crystal in the exact Laue symmetric position. And below, you have a diffraction pattern that is not in the exact Laue position. In this case, Q is equal to K, and in this case, Q is equal to K plus G. So the 3D dynamical variables R and K are decomposed in their 2D components on the image and diffraction, respectively ρ and Q. During the 70s and 80s, it has been developed the description of dynamical electron diffraction through the approximation of a Schrödinger-like equation of a two-dimensional object moving along the z propagation direction assimilated as the time parameter. And this Schrödinger-like equation is like that. In electron microscopy, samples are have small thickness, and therefore the variation of the potential is approximated by a z average potential. So we do the second approximation, the projected potential. And we obtain this Hamiltonian that is the diffraction Hamiltonian. And you can see here where you have the term K square that I defined before. K square is equal to K0 square minus Kz square. And V bar is the projected potential. Here you have the diagonal elements of the Hamiltonians that corresponds to the kinetic energy that diverges with the large Q term. On the right, you have the limited diffraction terms that corresponds, in the case of crystal, to standard structure factor formula. So now we describe the diffracted intensity and the intensity of the image. At the initial state, at z equals 0, you have a two-dimensional electron that has the plane wave key, and then after the samples, the plane wave becomes a psi of z at the thickness z, and this is a function of the eigenvectors and eigenvalues of the Hamiltonian H. This is the expression of the psi of the state psi. When you project this state on the Q vector that is located on the diffraction, the reciprocal space, you obtain the diffracted intensity here, that it comes from this expression. When you project this state psi on the real space, you obtain the intensity of the image, and you have to include the optical transfer function of the microscope. So, on the right, I present you simulations of high resolution along the five-fold direction of a high-resolution electron microscopy image of the icosahedral phase aluminium, palladium, manganese. I don't talk about now the model of this phase. I talk about the model later. And there is the corresponding diffraction calculated, the calculated diffraction. The computation is performed at 200 kilo electron volt, and I use 461 beams that are shown on the diffraction pattern. The thickness of the foil is 5 nanometer, the defocus is minus 50 nanometer, and the optical aberration parameters are the following. So, the only condition required to apply this formalism is that the set Q of the wave vector is an enumerable set. This is the Hamiltonian diffraction. So the Hamiltonian diffraction can be written as a matrix, and therefore there is a limited number of rows and columns, and therefore we have to do a cutoff of the Q bases. So this condition is satisfied for crystal as they are periodic. We can do a cutoff anyway because the Q basis is periodic. The situation for quasicrystal is rather different, as the Q basis is a downset. But it is possible to perform a cutoff that takes out the wave vectors with large Q perf, and therefore with very insignificant intensities. As a consequence, there is no need of artificially introducing large crystalline supercells in the dynamical calculations of quasicrystals. Now I show you the evolution of the intensity of the central beam as a function of the thickness for various Q bases. So I recall the 6D diffracted Q vectors as a parallel component and a perpendicular component. On the left, we have performed calculations for the maximum value of Q perb that is equal to that 2 plus 3 tau. and the parallel components of Q changes from this value that corresponds to this large dashed line to this value, 13 plus 21 cho, that corresponds to this continuous line. And the intermediate value corresponds to finer dashes. On the right, you have the evolutions of the beam, the central beam intensity as a function of the thickness, but with the maximum fixed value of Q parallel that is equal to 13 plus 21 cho, and the Q perp change from 1, this large dash line, to 2 plus 3 to. We can notice two things. The first thing is that the Q basis is chosen with large parallel bond, and the perpendicular bond is smaller. This is consistent with the experimental diffraction pattern, where the peaks with large perpendicular components have too weak intensity to be observed, and therefore the observed peak on the experimental diffraction pattern form a discrete set. That's why we can apply this formalism. The other things that we can notice is that in this right part of the intensity, the evolution of the intensity is periodic for this large dashed line. This periodicity is due to two important truncation in the Q basis, and especially in the perpendicular component of the Q basis. So we have to introduce beams with large perpendicular components, even they are not observed because they have too weak intensity, because the large perpendicular components of the Q basis enforce the quasi-periodicity. By these large components, we can see the main feature of the quasi-periodicity in the solid. What are the differences between the crystals and quasicrystals about this formalism? In the case of crystals, the Q basis is enumerable, and the projected potential is the usual structure factor for the diffracted vector Q prime minus Q. In quasicrystals, the main problem in computing the eigenstates of the Hamiltonian is the numerical stabilizations of the values when increasing the size of the Q bases. Contrary to crystals, Q bases of quasicrystals. So, you have the term that is also different to crystals is the off-diagonal terms of the Hamiltonian. These terms, Q, V bar Q prime, that is V bar of large Q with this parallel and perpendicular components. You have this expression where omega is the volume of the unit cell in the hyperspace. K is the number of the different atomic surfaces located at the site RG. K of Q perp is the Fourier transform of the atomic surface, and Fg of Q parallel is the form factor of the different chemical species attached to the atomic surfaces. Now I want to describe the skeleton model of the icosahedral atomic structure of type F. I recall that the type F corresponds to the unit cell in the hyperspace that the faces as occupied by atoms. Some models use the fitting parameter and more than 100 of fitting parameter. The fact that we use the fitting parameter, it's difficult to correlate the structural model with the physical properties. So here we present a model of an ideal quasicrystal without any fitting parameter and without any small distances and as simple as possible, and with a minimum number of different chemical configurations. And we want that our model infer some physical properties such as magnetic properties. And we want to compare the model with the experimental results, such as density, composition, and diffraction data of X-rays and neutrons. So we put these three atomic surfaces that are bounded by mirror, that are triacontahedron, so they are bounded by mirror, and this geometrical constraint, topological constraint, are issued from physical constraints, which are local matching rules and easy Phasian relaxations. So we put this large triacontahedron on the odd, the even node in the hyperspace, in the hyperspace N, and then we put this large triacontahedron truncated along the 5-fold axis to avoid short distances, and we put this triacontahedron on the odd sides N prime, and the small triacontahedron is put on the BC sides. Now I have to decompose the, we want to do a chemical decoration of this skeleton, and so we have to decompose each atomic surface in small pieces, and each pieces will be attached to chemical species. And we do the cell decomposition. So here you have decomposition in the perpendicular space, and here you have the corresponding cluster in the physical space. This cluster corresponds to the MM prime cluster. The MM prime, M is a cluster attached to the node N. M prime is an attached cluster to the node M prime. And we called this cluster like that in comparison to the Mackay cluster. In the case of the Mackay cluster, you have a small icosahedron with an empty vacant seat at the center, and then the icosahedron and a larger icosahedron. For the M and M prime cluster, you have the small icosahedron is replaced by a partial occupied dodecahedron with a center, and then the icosahedron and the large icosahedron. And we applied the cell decomposition. That means that two atoms in this cluster are issued from two atomic surfaces, the projection of which in the perpendicular space have a non-empty intersection. So to know where are the atoms in the cluster, you have to study the intersection of the atomic surfaces in the perpendicular space. Here you have these 7 cells, and if you merge these two cells, C1 and C2, you obtain these cells omega, and this cells omega corresponds in the physical space, distribute in the physical space nodes that are located in the center of the cluster. If you merge these 3 cells, C2, C3, and C4, you obtain this cell alpha, and this cell alpha distributes in the physical space atoms at the vertices of this icosahedra, and so on. So omega, alpha, beta, and gamma are the only ingredients needed to describe the chemistry of the icosahedral phase. This is a unique 6-dimensional structural model for the description of the icosahedral phase, aluminium, palladium, manganese, and aluminium, copper, iron. On the left, in color, you have the chemical decoration of the atomic surfaces, and on the right, in perpendicular space, and on the right, in gray, you have the chemical decorations of one of the MM prime clusters in the physical space. In this space, there are only 2 different chemical configurations from MM prime cluster, and 1 configurations with 82% of partition. And here we have also B and B prime clusters, and we have only 9 different configurations for the B and B prime clusters. B prime clusters are clusters close to the Bergman clusters. So here in the perpendicular space, you have the chemical species in brackets. On the left, you have the chemical species of aluminium, palladium, manganese, and on the right, you have the chemical species of aluminium, copper, iron. So in the case of aluminium, palladium, manganese, the N atomic surface is occupied by aluminium, with the exception of the cell alpha that is occupied by manganese. The N prime atomic surface is occupied by palladium, with the exception of the atomic surfaces beta and gamma that are both occupied by aluminium. And the BC atomic surface is occupied by palladium. And below you have here the volume of each cell. We can see, and here you can see that the M1 cluster is composed by a center of aluminium, then a partially dodecahedron occupied by aluminium, and then an icosahedral occupied by palladium, and the large icosahedron by aluminium. You can see that all shell of the cluster are occupied by only one unique atomic chemical species. And as an example, in the case of the manganese occupy only the alpha cell, and entirely the alpha cell, with the volume 8.29%, that corresponds to the 8.3 atom percent in the case of the experimental composition. And this manganese distribute in the physical space on this large icosahedron. So we will see. And note that in the case of aluminium, copper, iron, the composition of the iron is 12.5%. So in the case of aluminium, palladium, manganese, manganese distribute on a network composed of icosahedron linked by bridges in the form of square. And there is only manganese, and the distance between the neighbor atoms of manganese is a large distance equal to 0.48 nanometer. So if you remember that aluminium, copper, iron, you have 12.5% of iron, the iron atom are placed in smaller distance because you have 4.28% of iron atom more than the 8.3% of manganese, because this network exists only because of the alpha cell and then for the 8.3% of manganese. Now I present a comparison what we have performed between the structural models and surface analysis in the case of aluminium, palladium, manganese, in collaboration with Barish Unal and Patricia Thiel. We have performed the models with two occupancy parameters, X and Y, and we vary the values of X and Y from 0 to 1. Well, in the case where X and Y is equal to 0, the N atomic surface is occupied only by aluminium, and in the case of the other extreme case where X and Y is equal to 1, the N atomic surface is occupied majoritarily by palladium and manganese. And the results of this study is that structure with N atomics who has a surface atomic N that is occupied by aluminum plus a small amount of manganese, and with palladium confined on N prime and BC atomic surfaces, these structures are the best candidate that are both in agreement with bulk diffraction data and surface analysis. So as we have more aluminium in the N atomic surface, that means that 5-fold termination planes are occupied by aluminium and with a small quantity of manganese. And therefore, this study shows that 5-fold termination plates can be considered as a cut of the bulk structure. Now I show you two generalized simulations performed on aluminum, palladium, manganese, and with variation of defocus. Horizontally, you have the variation of defocus, and vertically, you have the variation of the thickness. Defocus vary from minus 50 nanometer to minus 30 nanometer, and thickness from 0.1 nanometer to 20 nanometer. On the left, you have a simulation. Both simulations are performed with 171 beams. On the left, you have a simulation performed on the spherical model, and on the right, you have a simulation performed with the polyhedral model that is presented here. The spherical model, two models have atomic surfaces located at the nodes N and prime and BC. But in the case of the spherical model, you have sphere at this node. The atomic surfaces are sphere with a partition with shells. In the case of the spherical model, you have short distances because of the geometry of the sphere located at the N and prime and BC atomic surfaces. In the spherical model is the model presented by Buddha et al. In 1992. On the N atomic surface, you have a small sphere of manganese surrounded by a shell of aluminum. The N prime atomic surface is a small sphere of manganese surrounded by a shell of palladium and a larger shell of aluminum. And you have a small sphere of palladium on the BC atomic surface. We can see that the two simulations are really close for small thickness. Under 10 nanometer, it's really difficult to distinguish the model because the simulations are really close. You can see again that we don't see the small distances, the short distances that are present in the spherical model, because remember that the simulation is performed with a projected structure, projected potential. Moreover, we have a limited resolution of the microscope. But at larger distance, you can do the difference between the two models and between the two simulations. So, as a conclusion, I can say that the dynamical calculation has to be performed with Q bases with large enough perpendicular components, because large enough perpendicular components are needed to take into account the quasi-periodicity of the materials. And we can do a comparison, differentiation between two models at large thickness, and we can use simulations for describe defects such as dislocation, because simulation and high-resolution electron microscopy image reveals the geometry of the materials.